welcome to our first workshop. I am pleased to welcome Juan Pablo Bernal, a professor at Autonomous University of Mexico, who is an expert in geochronology, and he runs a uranium thorium laboratory, first one in Latin America, and he's also expert in trace elements and other techniques. His main interest are changes in late Pleistocene. So thank you very much.
Thank you.
And the floor is yours.
Okay. Thank you very much. Thank you very much for all the organizers for inviting me. This talk I'm going to be telling you, it's a continuation of what Kathleen just discussed about. And she actually went ahead of me and asked for a raise of hands who has done any uranium thorium dating. So not many of you have done any uranium thorium dating, but now you have the basic principles of the dating, and now we're going to get more into how do you work with your data, how do you obtain your data, how do you work with your data in a more practical sense. So you can copy this QR code in your phones. There's a link to a Google Docs file, a Google Docs folder that will have several papers that are kind of basic papers that I'm going to be discussing, and 2 or 3 screenshots with data that I'm going to be showing you. So if you all have it, otherwise I can just send you the link later on. Okay, so what are we going to be discussing is how we measure uranium-238, 234, and thorium-230, how we actually do to calculate an age, what is the detrital correction. Kathleen, Kathy went through a little bit of detail of how to do it. We're going to get into a little bit more details. That's something that, if you're working with experience in science and something with uranium dating, it's basically something you cannot get around with it, so you might as well understand it as best as possible. And then we're going to be building some age models, which is also really, really good. This is basically an essential part of your work that usually, not always, but usually it's left in the supplemental material of your paper. So there's very little discussion of it. So a lot of it is it's coming from what I've learned from 20 years of doing uranium thorium dating, that sometimes it's difficult to understand the papers because papers have to be very condensed. So I've tried to put it on a more easy way to understand it. So let's start with how we measure uranium isotopes and thorium. Truth is that measuring uranium decay isotopes is not easy. Why is not easy? Despite of what we, if you go to a lab and they put it just straightforward, it's not easy because uranium is not very abundant. Uranium, if you have a stalagmite with 1 ppm of uranium, which is a reasonably rich uranium-rich stalagmite, it's actually, you only have this micromole of uranium-238. But if it's already in secular equilibrium, meaning that it has as much thorium-230 as it can actually have, you can actually make the calculations and see that you have around this concentration of thorium-230. So this is starting to be very, very low. So this is around 154 ppts, parts per trillion, of thorium-230. That amounts to approximately 242 billion atoms of thorium-230, which you'd say, yeah, it's a lot. But if you consider that the most efficient detection methods that we have so far only detect approximately 3% of the amount of material that we introduce, you are left with only 7 billion atoms of thorium-230, which might sound a lot. It's not, but it's enough right now to measure. And this is on the under ideal conditions. If you have, let's say, 50 ppbs of uranium in your samples, divide this by 50, by 20, and if your sample is a Holocene sample, then divide this by further divided by 10. So the amount of thorium-230 it becomes less and less and less that you can measure. So basically, you need either a lot of sample or a very sensitive method. Historically, it was measured by what is called counting methods, alpha spectroscopy. So alpha spectroscopy, Kathleen gave you a little introduction. It's a method that is actually counting the alpha decay events of uranium-238, uranium-234, and thorium-230. For that, you need, it basically relies on the radioactivity of these isotopes. And uranium-238, even though it's a radioactive element, it's not very radioactive. Uranium-234, it's also radioactive. It's more radioactive than uranium-238, but also not very radioactive. So sensitivity in these methods it's a problem. Basically, what you do is you dissolve your sample, and you just, one way or another, you just put it on an aluminum plate, either electrodeposited, or you can absorb it into manganese oxide, but it has to be a very thin layer, and has to be, there are many aspects to be considered. And then you have a counting instrument. This is a do-it-yourself school alpha spectrometer. This is a little bit more professional one from Ortec. These counting instruments are still used for other purposes, not much anymore for uranium dating, but usually you leave your sample counting for 1 week, something like that, to have enough counts for uranium. So if you have to date 25 samples for your stalagmite, just start to add up. There's a further problem with that. Sample size you need, in the ideal conditions, between 1 and 10 grams, and that's just for measuring uranium-238. Counting times are long. And then there's another issue. Sensitivity is not related to the relative abundance of the isotopes, but rather to how radioactive they are. So you can see here, this is an alpha spectrum of uranium-238 and uranium-234. They are fairly similar in sensitivity-wise. Problem is that once the counting statistics are considered, they are very similar, and therefore a property called error correlations become very, very important. I'll show you a little bit later what the error correlations are. So this is how things used to be dated in the 60s, in the 70s. There's a nice picture of Henry Schwartz. I couldn't get a hold of it. Henry Schwartz was one of the first persons dating stalagmites. And there's this stalagmite with a big hole in it that was basically just scraped out. They were probably taking about 40 grams of calcite just to get one date. So because of this method is pretty much no longer used for what we are interested in. Now we're working with mass spectrometry. For those of you just coming into the field, you'll soon realize that mass spectrometry is a workhorse of speed lithium research. So we use mass spectrometers for dating, we use mass spectrometers for oxygen, carbon isotopes, or uranium isotopes, or calcium isotopes, or whatever isotopes you're measuring. We also use the dating mass spectrometer for trace element analysis, for laser ablation. So it's basically you will be working with a large variety of mass spectrometers. So basically, a mass spectrometer is an instrument that allows the separation and quantification of ions as a function of their mass-charge ratio. Basically means that there must be a way that you have to ionize uranium or thorium or whatever element that you're interested in, sometimes even molecule, and you analyze and you separate those ions based on the mass to charge ratio. You have your sample, and your sample basically has to be introduced into an ion source. That ion source might be or not within a vacuum chamber. The rest of the instrument is at really high vacuum. You have, after the ion source, you have a system that focuses the ion beam and shapes the ion beam, and then puts it into a mass discriminator, which is usually a magnet, but could also be a quadrupole. And then you have a detector system. A detector system is something that is going to give you a digital signal proportional to all the to the amount of ions reaching that detector, and could be a Faraday cup, channeltron, secondary electron multipliers, dailies. There are plenty. The ones we're going to be working, I'm going to be talking about mostly are either thermal ionization or inductively coupled plasma as ion sources. Mostly today most uranium thermal dates are obtained with ICP MS, and I'm going to tell you why in a minute. Even so that you can measure 238, 234, and 230 with a quadrupole, magnetic sectors are more sensitive and have lots of other advantages, and with all these detectors. So what is a thermal ionization mass spectrometer? A thermal ionization mass spectrometer is you do your chemistry. Kathleen showed you a little bit about the chemistry, and you put a little drop of your sample of your of the uranium that you have purified, and you put it in a filament, a tungsten filament or a rhenium filament. You put that filament in a vacuum chamber in the mass spectrometer, and then you heat this. You put a current through it, and it's just basically like an old bulb that you used to have. Exactly the same principle. And basically, what happens is evaporates, hits another heated filament that ionizes, makes an ion cloud. And this ion cloud, there's a set of extraction lenses. There's magnetic fields that are just pulling the ions into the mass spectrometer, and the magnet is actually separating the ions. And usually you get the lighter ions have what is called less momentum, less amount of less energy, so they are easier to detour, to change directions, while heavy ions are more have more momentum and therefore more difficult to detour, and therefore you can separate heavy from light ions. And this is usually what you get. These very, very nice flat top peaks. This is a mass scan for uranium 238, 236, 235, and 234. This is, of course, obtained from a brochure from one of the flyers. I think this is from NU. So it looks really nice. The advantage of thermal ionization mass spectrometry is, first of all, it was the first method to actually count the isotopes based on their real abundance and not the radioactivity. It's very precise. The results are very precise. It's very sensitive. The signal to noise ratio is very large and has a very clean mass spectrum. And this is very important because there lies one of the limitations of multi-collector isotope. It comes with a little bit of problems. One of them is that there is what is called differential ionization efficiency. Because you are heating the isotopes here, basically there's a distillation process going on here, and it's actually fractionating that. And that distillation process going on here, that also happens with oxygen isotopes, is modulated by the Rayleigh equation that you'll discuss later. But it's also time dependent on the analysis. And there's another very big problem. Not all elements ionize very well. For example, ionizing thorium is really difficult. when we were working with uranium thorium dating, when I was doing my PhD, and we were doing some things dating, basically out of 20 samples, 1 or 2 would fail because thorium will not one of the samples, because you have to heat the sample a lot. Sometimes the filament just breaks, and because it's vacuum, it's gone. You cannot do anything. So that's a little bit of a problem. Thorium is not the only one. There are some other elements that are difficult to ionize. But also because it's difficult to ionize, sensitivity for these elements is not the best. It's good. It's really good. It's enough. But it's not really the best. With compared to alpha spectrometry, you can get away with 1 gram, half gram of sample, and you'll get very decent phases. These are the sort of more modern instruments that you will find: the thermal Finnegan, the Triton thermal ionization mass spectrometer. In here, you'll have the ionization chamber, the extraction lenses, the magnet, and the detectors and the amplifiers, part of the mass spectrometer. This is from new, similar, very similar, different geometry. The current instrument will differ a little bit on the geometry, how much they're actually dispersing. They're differing on the ion optics, how efficient they are. They are also differing on how they're moving the detectors. Overall, the principle is pretty much the same for each one of the instruments. And now we have the current method that is actually used, which is inductively coupled plasma mass spectrometry. Here, the main difference is that we have a very efficient ion source, which is an argon plasma. An argon plasma is basically formed when argon is flown into within a radio frequency field around 40 kilohertz, and there's a spark just ionizing the argon, and these ions will stay here in this radio frequency field. Once we flow more argon into this, there will be a chain reaction of ionization, and then we can have a plasma. A plasma which are basically composed of ionized argon elements, argon ions, sorry. And then what happens when we put an aerosol of the sample? We volatilize the sample one way or another. I'll show you that there are several ways to create an aerosol of the sample. That aerosol is the sample dissolved, basically of the sample dissolved. Will have your uranium, your thorium, probably, and it would also have lots of water molecules. So the first thing that happens is this plasma is very hot. Around the base of the plasma could be up to 8,000 Kelvin, which is extremely hot. So as soon as the aerosol reaches, gets close to it, it'll evaporate. The water will evaporate, and all the particles, oxides, and salts of your elements will remain. Then these are decomposed, atomized, and then ionized again, and then these are extracted into the mass spectrometer. This is happening at atmospheric pressure, so there's air surrounding this plasma, and this is to 10 to the minus 5, 10 to the minus 8 torrs. So, and this is happening within 1 or 2 centimeters. So there's a very, very, very big change in pressure between here and here. So the ions start to expand, and that leads to some fractionation of the ions going. Why are we using an argon plasma to make the ions? Argon has a very high ionization potential, about a little bit above 1500 kilojoules per mole. Above that, there's only helium and neon, and fluorine. All the other elements have a ionization potential which is lower than argon. So that basically means that argon, when the elements are in presence of argon ions, the argon will ionize them. Argon will take an outer electron out of them, of pretty much all the elements in the periodic table. This is the ionization efficiency for all the elements. Most elements ionize that are introduced to the plasma. Most elements are ionized around, sometimes 100%. Some elements are not very effective, but are still ionized, depending on their ionization potential. So the plasma turns out to be a very efficient ion source. The mass bias, there's no even though that there's some fractionation of the isotopes, is constant. It doesn't is not time dependent during the analysis, in contrast to TIMS. And the other advantage is because the plasma is at atmospheric pressure, you can actually couple to different sample introduction systems like gas chromatography, like laser ablation systems, like liquid chromatography. But also, because the plasma is at atmospheric pressure and there's nitrogen, oxygen, CO2 nearby the plasma and actually diffusing into the plasma, the potential for some complex and molecular interferences is there, and that's something that we need to deal with when working with ICPs. There are currently two instruments that are widely used. One of them is the thermofinnegan Neptune ICP-MS, widely available in many laboratories, and this is the new Plasma 3 ICP-MS. There are previous versions of these instruments. You could find in some other labs the BG54 or the GB isoprof or the Plasma 2 or the Plasma 1 and from new. You will also find newer instruments that are coming into market from the last few years. The Neoma and the Sapphire, which have what is called a collision cell. I'm not going to get into the details of that. But as you can see, they are basically similar to the TIMS, except for two things. Both plasmas have first what is called an electric sector analyzer. And what the vendors will tell you is, they'll basically homogenize the energy of the ion beam. And I've struggled for many years to actually understand what they actually meant by that. What it actually means is that because you are introducing a whole bunch of elements, the ESA, what it's going to do is going to limit the mass range of elements that you're going to be focusing into the magnet. That's something that you don't have to do in the thermal ionization mass spectrometer. Why? Because it's in vacuum, it's everything as clean as possible, not in here. So you need this ESA to get rid of all ions that are outside the mass range that you are interested. Other than that, they have the same detector capabilities. They have the same magnets. It's pretty much the same electronics. And one of the things that we find here with multi-collector plasmas is that because they have a very efficient ion source, they are way more sensitive than thermal ionization instruments, and therefore it enhances the precision very well. So a little comparison between TIMS and multi-collector ICP-MS. In TIMS, you can work only between 50 and 20 samples per carousel. Once you run from your 50 and 20 samples, you have to take it out, put another carousel, and leave it vacuum overnight, and then start running again in the morning. Thorium, as all the high ionization potential elements, are very difficult to measure. So the low ionization efficiency leads to very low count rates, and therefore poor thorium-uranium statistics. So you basically can get away and get good data with 3 or 4 nanograms of uranium, with soft per mil uranium-234 measurements. And very important, uranium and thorium are measured separately. And why is that important? And why is that? Because uranium is volatilized at reasonably low temperatures, and thorium at very high temperatures. So you can run your sample at, let's say, 1200 degrees, and you analyze for uranium, and then you can probably, if your samples, if uranium and thorium are the same, then you can run it up to 1600 degrees, and then you analyze for thorium, and that works very well. Multi-collector SCP-MS, basically, because you don't have to be changing the carousel, you can run and run and run and run samples with an autosampler pretty much forever, and you just keep on feeding the autosampler to get the agents. Thorium is as sensitive as uranium, so that helps a lot with the statistics. You can get very good ages with only 2 to 3 nanograms of uranium. So you just have to start to visualize how many, the small amount of ions that we are actually detecting. Just 2 or 3 nanograms of uranium. It's just basically peanuts. And still get a really, really nice precision in your measurements. But of course, you want to keep your instrument running. You need to have lots of argon bottles to keep the plasma on, and a lot of acids and water. So they have their pros and their cons. So a small comparison. This is the half-lives. This data is from different papers. I'm comparing the uranium-234 to 38 values at secular equilibrium, from which the half-lives were deducted. And basically, these 3 measurements were obtained with alpha spectrometry. So you see, in the most ideal conditions, these are the precisions that you obtain. Ken Ludwig in 1992 measured with things very, very precise 234, 238 in uranium-nights, and got a hold on and proposed this half-life. So you can see a significant reduction in the uncertainty, but his half-life was never really taken into consideration because it had some other issues going on. Nevertheless, Hai Chang in 2000 made this made these measurements of 234 to 38 in sacred equilibrium, and this is the isotope composition that he reports for sacred equilibrium. And then he repeated this similar exercises with more measurements, but with multi-collector SCP-MS, and you can see the reduction in uncertainty, like really, really nice. This is also for 230 to 38 sacred equilibrium. You can see Chang et al. 2000. This is the best value that he can report. And 2013, 13 years later, with multi-collector SCP-MS, it's just 1 per mil, from 3 per mil to 1 per mil. And this is using TIMS, and this is using multi-collector SCP-MS. A more direct approach to what we're doing with the stalagmites. This is a paper from POSI 2019, and they have this stalagmite that was initially dated by TIMS and later on was dated with multi-collector SCP-MS. So there's a mixture of multi-collector and TIMS data. The multi-collector ages are red, the multi-collector SCP-MS ages are in red, and the TIMS ages are in black. Immediately you see that there's a little bit of a change. This is the age model for that stalagmite. And immediately you can tell that there's a change, there's a difference between TIMS and multi-collector SCP-MS. Why I like this example? Because they were run in the same lab, 2 different instruments, a stalagmite with the same amount of uranium following exactly the same chemical procedures. So I'm plotting in this axis the relative uncertainty age, uncertainty relative to the age, and you can immediately see that the TIMS ages have around 8% of uncertainty in this stalagmite, while the multi-collector are always around 3.5% of uncertainty. So this is a really nice example why multi-collector ICP-MS is now widely used for uranium-thorium dating. Teams ages are still good. They're still it's not that they're not valid, but it's way easier and more precise to get them using multi-collector ICP-MS. Now, before jumping to the analysis, there are two things that need to be taken into consideration for the analysis of uranium and thorium isotopes. One of them is the addition of the tracer for isotope dilution analysis, and the other thing is the separation and purification of uranium. So, how do we actually quantify uranium and thorium isotopes? We actually weight them. How we actually do it? How would we manage to weight something so tiny as a few picograms or femtograms of thorium using mass spectrometry and isotope dilution? What is isotope dilution? The isotope dilution is basically an analytical methodology where we are gravimetrically adding an internal standard with an isotopic composition which is different from the sample and is extremely well characterized. So what we need is something that has the same chemical and instrumental behavior as uranium, as the natural isotope of uranium and thorium, but they are not them. This spike, this tracer will also allow us to see if there is some uranium and thorium lost during the sample preparation, and we can actually control for that. And basically, it allows us to make a very, very high precision gravimetric analysis of these isotopes. For this, we need high purity thorium-229 and high purity uranium-233, or a mixture of uranium-233 and uranium-236. As Kathleen said this morning, these are synthetic, these are radioactive, these are way more radioactive than the normal natural uranium isotopes, so you have to be careful with them. I'll tell you a little bit later about it. These are when I mean that they are extremely well characterized, they have to come with some kind of certificate like this. These are the certificates for the spikes that I have for thorium-229 from Oak Ridge National Lab. It has to give you a little bit of an idea of how many uranium of the thorium isotopes present and the abundance. For the 233 spike that we have, it has to give us also an idea. That's mostly uranium-233. It's 98.02%, with the uncertainties pretty well characterized. The isotope ratios that are required, that are certified. So what we do, we are actually mixing two isotopically distant end members. So one of the things that I'm going to be talking here a lot here is mixing lines. So raise a hand. Any one of you knows what a mixing line is? Okay, yeah, very few. I highly recommend you to have a very basic geochemistry course because it'll help you a lot to understand what's happening here. And the mixing line is basically the result of mixing two different things and at different proportions. So, for example, this is going to be different. Who had coffee this morning? Everybody had coffee this morning. Most people. Who had sugar in them? Okay. So you had how many sugars? Two? One?
I should say 3 now.
3. Okay. So basically, thank you very much. Appreciate your help. So basically, what this had is a mixture of pure coffee and sugar at different proportions, and you can have and if you put them together, not mix them, but if you put them together, you have the equivalent of a mixing line between coffee and sugar. So it's kind of similar thing here. We're mixing a very pure thorium spike. This is a 229 spike with our sample, and we're getting a spike sample. So, yes, we're getting a mixture of our spike with the sample and different, and because we have this spike at a very well-known concentration, we can actually know how much of this mixture belongs to the spike and how much of this mixture belongs to the sample. The advantage of thorium-229 is that it will follow exactly the same chemistry as thorium-230. So if we lose a little bit because it got stick to the walls of the container or whatever, we're going to be losing thorium-230 at the same proportion of thorium-229. Because we're mixing them together, if there's a loose, if there's a drop that is accidentally lost during the analysis, we will be losing 229 and 230 at the same proportions. So that will actually help us to have a control of how much thorium is actually analyzed. And they have very similar, not identical, but very similar behavior in the mass spectrometer. So it's just a matter of disentangle this composition, and for that we are using a mixing equation of isotopes with different isotope composition. Fowle in the basic geochemistry book from 1997 put it very nicely. It's here, this is the equation, which is as a function of the amount of sample, the weight of the spike, the weight of the sample, the atomic weight of the sample, and the atomic weight of the spike. These are different because uranium-233 has a different atomic weight than than natural uranium. The abundances of different of the isotopes, the ratio that we are measuring, and the abundances of each isotope in the sample. So there's a book, Xu 1997, Quantitative Geochemistry, which has a really nice example. You can have it here. Using the same equation, we know the uranium concentration of in the spike. We know the abundance of uranium-233. We know the abundance of uranium-238 in the spike. We know the atomic weight of the spike. We know the uranium-233 in our sample is 0, not close to 0. It's 0. There is no uranium-233 in our sample. We know the abundance of uranium-238. We know the weight of the atomic weight of the sample. We know the weight of the spike because we are doing that gravimetrically. We know how much sample we weighted, and just doing some maths, we can actually obtain a concentration of a very precise concentration of uranium. And we can do the same for thorium, and then we can ratio the concentration. One advantage of this is that this is very precise. You can apply some other methods that that might be available, that are used in other techniques, but because we're measuring ratios here, this is extremely more precise measurement than measuring the absolute abundances of each isotope, and therefore these will come with an uncertainty of lower than 1%, sometimes even lower than 0.1%. So these are very, very, very precise measurements. The other important thing is that you need to separate uranium and thorium. You need to purify uranium and thorium. And this is extremely important for two things. One of them is that you cannot just dissolve the sample and put it into the mass spectrometer, into the multicollector. Why? Because because we are introducing everything that is in solution. So if we introduce a lot of ions into the plasma, they will ionize. They will go into the mass spectrometer, into what is called the ion optics. But they're going to cause something called charge space effect. So because there's going to be a lot more ions, because you're going to have all your calcium, all your strontium, all calcium, strontium, magnesium, everything that is in the sample. It's going to cause what is called space charge effects, and it's actually going to affect the fractionation of the isotopes, and it's going to affect your measurements. So we actually need to separate uranium and thorium. And separate uranium and thorium is easy, but it's a little bit, and it takes a little bit of work. We make sure that the samples and the standards that we're using are exactly in the same matrix. It also helps us to remove potential interferences that we might have. It also allows us to pre-concentrate the sample. If the sample is dissolved in 10 milliliters of acid, we can probably just have it in 1 or 2 milliliters. So that increases the concentration and therefore increases the counting statistics. And it basically includes a dissolution step, and then sometimes, not all the time, sometimes there's a co-precipitation. So basically what we do is we add some iron into the dissolved sample, and then we add a little bit of ammonia, and that actually precipitates the iron hydroxide, and the iron hydroxide will suck all the uranium and thorium, like really, all the uranium and thorium will stick into the iron oxide, like really quantitatively, really nice. Then this is dissolved, redissolved, and using ion chromatography with different kinds of resins, we actually separate, we can just get rid of the excess of iron, and then we can separate uranium and thorium following a procedure like this. So one of the things that I need to tell you is that sometimes when you go to a lab, you'll say, oh, you just follow this procedure and as they say, and Bob's your uncle. The thing is, someone spent a fair bit of time actually getting uranium and thorium separation. And this is how they actually look, these calibration curves. This is from my lab, this is from another paper. Basically, you need to know exactly when uranium is being coming out from the ion chromatography columns, and when the thorium is being eluted, and when other potential elements that are potential interference are being separated. So there's a fair bit of work to getting all these prepared. So now we have uranium and thorium separated. We've already put it through the mass spectrometer, and boom, you got your data. How did we get from this to here? And this is going to take us a good part of the next hour. You have your data, and you have uranium and thorium concentrations. When you're looking at your data, you want as much uranium as possible and as little thorium-232 possible. Why? I'll tell you in a second. They're going to give you a thorium-230-232 or uranium-238-232. Depends on the lab. They're probably going to give it to you either in activity ratios or in isotope ratios. You have to make sure what is the lab actually reporting. The highest of these ratios, the better, because it means lower the trityl thorium-230. And I'll show you why in a second. These are the activity ratios that are going to be used for age calculations, but these activity ratios are just going to give you the first approximation of your age, not the real age. Why? Because this age has to be corrected for the trityl contributions, so you get some results of the isotope compositions corrected for the trityl contributions, and the actual ages or the ages of your sample. So we're going to go through all this table, through the concepts of this table with a little bit more detail in a second. And I think you can have this table. It's in the link that I sent you. So now you have these ages. Let me show you a little bit of the ages of these equations. There are three solutions to the uranium-238 decay series. These three solutions are essentially the same. They're just basically a change in the algebra. This is the first equation that was originally used by Wally Brocker, by Eric Hendy in the 60s and 70s, and a little bit during the 80s. It's based on 230 to 30, uranium 230 against uranium 234, and 234 to 38. These are the K constants. There's a second equation. Kathleen mentioned that it is the Edwards equation, that it is basically 230 to 30 uranium 238, and the delta uranium 238, uranium 234, sorry. And a very similar equation, which basically converts the delta 234 into activity ratio. Very, very, very important. If you try to solve this equation for the age, you're going to be spending the next 75 years. You cannot solve this equation for age. Why? Because you have age here in the age in time in this part of the equation and in this part of the equation, and basically there is no way to actually solve to get a function of time as a function of isotopic composition. So what do? Either these are the graphical solutions of the of each equation, and I'm sorry, it used to look better in my computer, but this is 230 to 34 against 234 to 38. This is 230 to 38 against delta uranium 234, and this is 230 to 34 against 230 to 38 against 234 to 38. So in theory, all the isotope compositions should, if you have one of isotope composition that solves this equation, then you should be able to get exactly the same result for this age. So what you can do is you just put your activity constant ratios in this plot, and it'll give you an idea of how old or how young your sample is. So it'll tell you, oh, I have this composition. Yeah, this is somewhere around 75,000 years old. But it'll give you an idea. But it's not really what we really want. So to actually solve the equation, we need to have the isotope compositions that we measure, and we have to solve this equation by iterating different times until we can solve this equality. And basically, that's the way most that's the only way to solve it, by iteration. Just basically by kind of guessing, by guessing which age is going to allow us, which age number is going to allow us to solve this equality. And using the K constants. And basically, that's the way to do it. But I'm sure that this doesn't give you more light. So how we actually do it? There are several softwares to do it. You can actually do it in Excel. You can do it. You can write software. But there are two main options to actually get the ages. Two softwares that are very, 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 very easy to work with. One of them is Isoplot, and the other one is Isoplot R. Isoplot was developed in the 80s and 90s by Ken Ludwig. He used to work first at the U.S. Geological Survey and then at Berkeley Geological Center. He was very, very good at programming and getting all the codes to solve geological equations in Excel in a graphical way. Problem is that Ken Ludwig retired, and not only that, but Microsoft stopped allowing to run. It does not allow to run any more Visual Basic scripts in Excel. So you have to work in Isoplot, which you can still get. I'll show you in a minute where. In a 2003 version or earlier. Sorry, 2013 version or earlier. So it's becoming more and more difficult to actually run it, because I tried to run it, some examples for this talk, and it's getting more incompatible with current versions of Windows. And you couldn't run it on a Mac. That's the other. But it's the first software that has actually provided a graphical interface to actually calculate the age, and included most geochronological systems, and it allowed for the correction of the detrital material. It was very transparent, very flexible, really nice piece of work. And you could get plots, what I call R2P plots, which are ready to publish, are like really nice plots. And if you look at the papers, your chronological papers from the 90s, from the 2000s, even from the last up to 2015, something like that, you would see plots that are just basically came out in papers, just the plots that came out from isoplots, like really nice plots that you could work with. But because here isoplot is getting more and more difficult to run, Peter Birmish from University College in London wrote an R-based code based on isoplot, but it's a different code from isoplot, and it has most your chronological functions, not all of them, and very importantly, is web-based. So I'll show you in a second how does it work. This is the isoplot. This is where you can get isoplots from Virtual Geochronological Center. Just a piece of advice: if you Google isoplot, don't go for the first link, because there's another new plugin software that is nothing to do with this version of isoplot. So in isoplot, you had your Excel spreadsheet and this set of options that were coming with Visual Basic macros and things like that. And you have this window. This was the main window from isoplot, from which you could get all these isotopic systems. Uranium, lead, argon, rubidium, strontium. It was really complete. So, and you can get these very nice uranium thorium evolution diagrams, like extremely good plots. I mean, this is definitely ready for publication. You could get a good detrital corrections, particularly because some of the methods for detrital corrections were also developed by Ken Ludwig, who really got into the maths of the corrections. And I'll show you in a second why you really need a good software to do it, because it's something that it's difficult to do it by hand. Not impossible, but time consuming. Isoplot R, on the other hand, is this. You can find it here in this web address, and this is the interface that you come here and that you start working. And I'll show you in a second how does it work. There are several mirrors in different parts of the world, which is good for most things. There's one in Austin, one in California, one in London, one in Europe, one in South America, one in India, one in China, two in China, and one in, I think it's actually 3 in China. So you have mirrors in several places, and that's really good because it's very reliable that if one server is down, you can work in other software. Sometimes you find that the version in London has more capabilities than the version in Austin or the version in South America. Why? Because sometimes it takes some time for these systems to be updated. But other than that, are pretty much identical. So this is how it looks like. You have, once you go into the interface, you have your data. You have always an example data. Here you can choose your chronological system that you're going to be working. The different options, and there are always options. We're going to go into these options with a little bit of time because they will list the details really. And there's help, and this help is actually really nice because it'll tell you exactly what, at least from my perspective, exactly what the questions that you might be having. Should I click here? Shouldn't I click here? It's really helpful. So for uranium series, this is how it actually looks. This is a simplified notation, but it's actually asking you for the 238 to 238 activity ratio and its uncertainty, the 234 to 38 activity ratio and its uncertainty, and the 230 to 38 and its uncertainty, and then what's called the error correlations. Error correlations, for the most part of the work that you're going to be doing, can be considered zero. And I'll show you in a second, once I show you an isochrone, what the error correlations might look like. So this is data that you will always find, you can already find in one of the Excel files that I put in this link that I show you. So then you have these methods. You can go to evolution. You can have an evolution diagram, which is the one which is something like this. You can actually make isochrones, and I'll show you in a second what an isochrone is, or you just can calculate ages. And because that's what you're interested, you just calculate the ages. So you go to the details, to the options, and this is very, very important for you to understand what you're working with. First, the input format. There are many ways to actually put your data, and you have to be very careful that your data is in this format. Labs usually sometimes report isotope ratios, sometimes they report 234 to 38 in activity ratios, sometimes they report it in delta values. Sometimes they report 238 to 232 isotope ratio, sometimes they report 238 to 232 in activity ratios. So you have to be absolutely certain of what kind of data is the lab reporting. And you put the data in the way the software is actually it's also asking you for the input errors. This is a discussion that is never going to be ending between different brands of mass spectrometries, whether you want to work with one standard error or two standard errors, whether it's more correct to work with one or two. Your uncertainties looks better if you're working with one standard error. They're more realistic if you're working with two standard errors, so you have to be careful with that. And also the output errors, whether you're going to be working with one standard error, two standard errors, or confidence interval. So we're going to go through these details, make sure your data match the input format. This is particularly important for this, and this also includes the uncertainties. Make sure you correct that. This is the different, so actually some labs actually also report the uncertainties as a percent level. You have to make sure that you're not introducing a 0.1% error, which might be a very good error, and put it here because put it as an error on activity ratios, because a 0.1 activity ratio uncertainty is rather large. So you have to be you have to be sure on putting your data. The output errors, again, I highly recommend you. Highly recommend you to work always at the same uncertainty level, 2 sigma level. So I would recommend you to work on 2 standard errors. But that again, it depends upon yourself to decide. What it is extremely important is that you be consistent. If you're going to be working with one standard error uncertainties, you have to be always working with one sigma. You don't change it in your data analysis. And if you go to ages, this is actually data from one of my students, stalagmite from Guatemala. You are not doing any detrital correction just yet. You just click run, and in a matter of seconds, boom, you have your ages. You have your ages, and these ages are in kiloyears with their corresponding uncertainty, and you have the initial 34 to 38, which Kathleen talked to you earlier, which might or might not be relevant. The initial 234 to 38, the uncertainty, and the covariance between age and 234 to 38. I'm not really gonna get into this, into the meaning of this. The important thing is that now you have time. You have your initial ages, but these ages are still not valid. So you have a lot of work, but they have to be corrected. Why they have to be corrected? Because of thorium. And why because of thorium? Because thorium is elastic. You need to do the detrital correction. So back to this table. In this table, thorium-232 is non-zero. It never is zero. There's always some thorium-232. And if there's some thorium-232, it basically means that there were the geochemical conditions to mobilize thorium, whatever the isotopic number, whatever their atomic mass, sorry. So basically means that if there's thorium-232 being introduced into your sample, there has to be some thorium-230 getting into your sample as well. And the geochemical conditions were set for at least some mobilization of thorium. So you have to bear that into consideration. So that basically means that for most stalagmite samples and for most uranium-thorium dating, if you're going to be dating some coral, this is also the case. At T0, thorium-230 is not zero. There's a tiny little bit or a significant part. Where? How much? We don't know. We really don't know, and we need to find out. Because otherwise, the ages that we are reporting are just basically meaningless. What is the effect of having more thorium-230? Is that basically the samples are older than the ages that we're obtaining are older than they should be. So basically, what's happening? This is the thorium-230 that we're measuring. Part of it, a little tiny of it, is coming from thorium-229, and we can actually subtract it quite nicely. So this is the thorium-230 that is present in the sample. But from this, I cannot tell how much was formed radiogenically in situ and how much was incorporated. Was this much? So how much was formed in situ? How much is detrital? Where do I draw the line here or here? There is actually no way to actually know it just by looking at thorium-230. But if we look at thorium-230, if we know that thorium-232 was mobilized too with thorium-230 at a reasonably constant ratio, we can actually use thorium-232 as an index for thorium-230 detrital. And we can assume that this ratio will be constant throughout the stalagmite growth. This is not a new problem. This is something that has been working from the 70s, from the 1970s, from the 1980s, up to a few years ago. This is actually being studied quite significantly, and I think you'll find most of these papers on the folder that in the mixture. So they can form what is called a mixing line. And this mixing line will allow us to determine either the most likely isotopic composition of the detrital material that we can correct our samples, or estimate the composition of the detritus-free sample, or sometimes even both. How we do it? We need to have 2 or more samples that are coeval, basically mean that they're around the same age, that precipitated with different proportions of detrital material. And we also need to know, make sure that the detrital material is not changing, the isotopic composition of the detrital material remains constant, and very important that all of them behave, all the sample behaves in a closed system. Basically means that there are no loss of uranium or no gains of uranium once the system crystallizes, because otherwise. So there are different types of isochrones. two-dimensional isochrones, which are very good to obtain the isotopic composition of the detrital material, sometimes of the autogenic material. I'll show you some examples. And there's 3D isochrones from Ken Ludwig and Titterenko. And basically will give us the isotopic composition of the detritus-free sample. Of the 2D isochrones, there are two types, Roshold type and Osborne type. Roshold type are those that are normalized against thorium-232, and Osborne type are those that are normalized against uranium-238. Then there are two types of Roshold. This one and these two. And these two types of Osborne. So I'm not going to go into detail, much of them. All of them are mixed lines, and they're just differing on the way how we're applying the isotopic composition. But all of them are a mixed line between autogenic and radiogenic end members. Autogenic end member and a detrital end member. They are exactly the same principle. In the Roshold isotopes, basically the slope of the isochrone is the isotopic composition. If you are plotting 230, 232 against 234, 232, the IEA slope will be 230, 234, and we can calculate the slope from the isochrone with a normal regression, with many of the regression methods. I'll show you in a second. And we can actually calculate 234 to 38 for the autogenic phase, from the 234 to 38 to 38 to 38 to 34. Look, these are all normalized against thorium-232. And then on the Osborne type, actually we can do it the same, and you can actually in the spreadsheet, in the files that I send you, there's a spreadsheet that has the same data, ready to be plotted either in Roshold or in Osborne isochrones. In Osborne isochrones, from the intersection to 0, we can get the isotopic composition of the autogenic phase. For example, from these isochrones, we can actually get the isotopic composition 230 to 34 against 234 to 30, and using this equation or this graphic, we can actually calculate the H. So the whole idea is to actually know 230 to 32 of the detrital material that is being incorporated into our sample. And there are three main ways to actually do this. One of them is assume a composition, the other is calculate using an isochrone, and the other one is measured independently and correct. So we're going to be discussing these three methods very quickly. Again, these are two mixed lines, assuming that we have an autogenic and DRT part of it. And basically, the whole idea is that if we assume that the thorium-230 that we're measuring in the sample is the thorium-230 radiogenic and the detrital, we can, and knowing the isotopic composition of the detrital phase, we can actually calculate the thorium-230 in the detrital phase, and then actually subtract it from the measured 230 in the sample. The first way to do it is actually assume it, and again, Ken Ludwig started with this method, which is basically, let's say, okay, I don't know the isotope composition of the detrital material, but I know that this is being measured at the Earth. So we know the elemental composition of the Earth. There are people working on the elemental composition of the Earth, and the elemental composition of the Earth crust has been Ross Taylor and Stuart McLean worked a lot in the 1980s, and they actually determined that the thorium-238 to 32, sorry, this is 238 to uranium, is for the crust, the average composition is 3.8 plus or minus 2. So it's a large. So what Ken Ludwig said, okay, we can assume that the detrital composition is very likely to fall within these limits of uranium and thorium ratios. And we can assume that it is at secular equilibrium or very close to secular equilibrium. So we can assume that it's going to have this uranium isotope composition, not isotope composition, activity ratios of 1 plus or minus 0.1, plus or minus 1%, which is reasonably, which is quite large actually, and 3230 to 38 also very close or at secular equilibrium. And this is the main assumption that we are doing. So, applying a little bit of maths with this, we can actually know the isotope composition, the thorium-230 to 32 of the detrital material, of the if it has the average composition of the crust. And also in the spreadsheet, there's one. In the files, there's an Excel file with a very quick calculation of how to get this number. So you can get a whole. So that basically means that 230 to 32 detrital has this isotopic, this activity ratio. So we go back to isoplot, and we're going to calculate the edges. And now I'm telling him, assume initial isotope composition, and I'm showing this isotope composition, and boom, propagate the uncertainties. This is very important. Always click on propagate external uncertainties. And these are the corrected, the uncorrected edges versus the corrected edges. As you can see, the edges, the uncorrected edges are a little bit older than the corrected edges. Sometimes the correction might be a little bit too small. Sometimes it's just a few years. Sometimes it's 15 years. Sometimes it could be 100 years. Sometimes it could be, for example, in this case, it's about 70 years, something like that. The important thing is that the corrected edges are younger. Why? Because we have subtracted the detrital thorium. There are two things. The corrected edges are younger because of that, but they also have larger uncertainties. And why is that? We have a 2-point isochron, and this is our sample. With this, this is what we are measuring. And this is the average composition of the air crust, and this is a big circle. Basically, when we are projecting our the composition towards the detritus free fraction, this is zero. This is zero. Zero in this axis basically means that there is no thorium there. Basically, the uncertainty has to be is actually larger. Why? Because we have a large correction. The uncertainties in the detrital material are large. So this is what is called a 2-point isochron. Sorry, because we have 1 point, 2 points, and boom, we have a detrital correction. So this is really a 2-point isochron. This is the simplest way to actually correct our edges, and it works really nice with samples with low thorium-232 or very large thorium-238 to 32 or very low 232 to 38 ratio. Probably 95% of the records that you'll see published use this approach. Probably, I mean, yeah, sometimes probably even more. Some records probably shouldn't be corrected that way, but anyway. But it basically works like a charm. It's a really, really nice correction. It works until it doesn't. And when it doesn't work, when the isotope composition of the detrital material is outside the circle, which is either not within the composition of the average composition of the air crust, not in circular equilibrium. Yeah, basically that is when it's here. And this is when we're starting to run into more tricky situations. How do we deal with this? We actually calculate it using either isochrons or measure it independently and correct it. So we measure it independently and correct it, and Kathleen mentioned some examples. We can do it either doing leaching experiments of the soil, doing cave monitoring and see and measure the thorium composition in the drip water, the bedrock analysis, and then in isoplot, we actually can put all the composition of the detrital material. And actually, the way it works is, now this is not working, but we have a very precise characterization of the detrital composition. And because it's very precise, what used to be something like this is now a more correct. It'll provide a more correct composition, with a significantly better uncertainty. And that basically has the advantage because if the correction of the detrital material is quite significant, if the age corrections that we are obtaining, if the contribution of the detrital thorium are significant, that basically means that if we want to obtain good uncertainties in our ages, we have to work in characterizing the detrital input. So I'm going to show you an example. This is from Partin, 2007, published in Nature, and Caroline, 2012, published in Science. These are stalagmites from Bernal, which were really, they were dated in Caltech. I mean, when you look at the details of this work, it was really a pain to actually date them. But they actually made a very nice job in dating these stalagmites. Why there were a problem? Basically, as Kathleen said, and I cannot stress it enough, always look at the supplemental material because there's always very interesting information about the data. These stalagmites have 3 problems. And these are problems which are not uncommon, actually. Very low uranium concentrations, which are not different to many other stalagmites. They have around 50 ppb of uranium, up to 100 ppb of uranium, up to 1.5 ppm. But they have very low uranium-234. And because they have very low uranium-234, the production of thorium-230 radiogenic is actually is actually depressed. It's actually very low, and they have high thorium-232, which basically means that there's a lot of thorium-230. There's an incorporation of thorium-230. So basically, there's a significant bias on the ages if they are not correct. So how did they work? Basically, they in some parts of the stalagmites they collect coeval aliquots from different parts of the stalagmite. Basically means that for one of these bands they actually collected 3 or 4 samples for each band. No, not for each band. For some bands, for some sections of the stalagmites, like here, and here, and here. And I think somewhere around here too. And Partin actually plotted isochrone, Roswell type isochrones, while Caroline plotted Osmond type 2 isochrones to actually calculate the isotopic composition of the autogenic material. But this is the isotopic composition of the autogenic material here, here, and here. But this is not the isotopic composition of all the stalagmites. But what they actually did is, with this composition, they can actually calculate the thorium-230-232 for the detrital material. And they can actually see how different it is in different parts of the stalagmites. So these are the Roswell isochrones. So what you're seeing here is the data from Partin. And you don't see that these activity ratios are plotted in like a cross or like an oval, something like that. They actually look like basically like a line. Basically, if you look at it very, very carefully, you'll see that these are very extremely long, elongated ovals, like really, really, really long ovals, and they are tilted. Basically, what I mentioned about error correlations earlier is because the uncertainty here in 238 to 232 is actually correlated with the uncertainty of 230 to 32. Why? Because the uncertainty here, the uncertainty of 30 to 32 has to be reflected in both axes. So that basically means that the correlations, that the uncertainties here, so that basically means that the uncertainties are correlated, and it has to be considered for the statistics. I'm not going to go into the details, but that's one of the things that has to be done. Yeah, so they actually calculated from the slopes here different compositions for the autogenic material. And in Caroline 2012, and why I'm comparing this because they are from the same cave, they're actually doing this exactly the same thing, but using Osmond isotopes. You can find the data for these plots also in the file that I sent you. And they actually calculate the data for the autogenic phase and the detrital. So taking the data from parting, from some that you can do it here, they actually go to an isochron, the uncertainties levels, the output errors, and the correlation. We are going to be using what is called a maximum likelihood. It's a robust form to actually consider the uncertainties in the x and y axis for a regression, and we're going to be calculating the Roswell isochrons, propagating external uncertainties. I'm not using the error correlations here, and this is how they actually, once you put it run, it takes like 2 seconds, and this is how they actually look like. And this is cut, but anyway. And what they actually do is you can calculate the composition of the autogenic material, or you can ask Isoplot to calculate the composition of the detrital material. And you get the calculation of the detrital material. You can do the same thing for the Osmond isochrons. Look, they look completely different. Same data set, but the isotope composition is very similar. So it's two different ways to obtain exactly the same information. Why was this important? Why they have to go through all this effort? This is the summary of the thorium-230-232 that they were the atomic 230-232 that they were obtaining on different parts of the stalagmites. These are the different values, different stalagmites, and this is the composition of the crust. So basically, actually, sorry, this value here is not correct, but this value is actually correct. Oh no, sorry, this value is in ppm too. Yeah, so as you can see, the isotope composition of the detrital thorium is very different from what you can obtain from the crust. And this, why they go through all the effort? Well, basically because they made all the trip to Borneo and they only had one chance, but also because with knowing this isotopic composition, they can actually obtain more precise ages than using the composition of the crust. So, what the lessons they learned, basically that thorium-230, 232 can be and is usually different from the crust, and when you have stalagmites with large concentration of thorium, this becomes very significant, very, very important. There's a problem with 2D isochrons, and one of them is that they are not completely independent from each other. 230, for example, this type of isochrons, 230 depends on 234, and 234 is actually in these two axes, so they are correlated in a complex way. They are not completely independent. Also here, they are correlated. So the data points are not completely fully independent. So one dependent on each other, but actually they are treated as independent. So that's not completely correct. So what can logic came in 1994. It basically, this is the normal evolution plot that you have. So basically said, okay, this is the age of my sample. What I'm going to do is this is the detrital-free composition. So basically, he said, okay, this is the composition. I'm going to add another axis, and this axis is 232 to 38, like in an osmotic isochron. And this 232 to 38 is going to, the detrital composition is somewhere around here, above this space, above these planes. Sorry, this is 0, so this is the detrital free, and the higher you go, the more detrital material there is. So this is the autogenic composition, the detrital free composition. This is the detrital composition, and if you have coeval samples, they will form, and again, a mixing line between these two phases, and then it's just a matter of getting a regression, a three-dimensional regression. In reality, what we have is three different, we have the coeval samples, and we can project that to get the composition of the detrital-free sample, basically where 232 to 38 is equal to 0. And with the idea that the detrital composition will be somewhere over here, over here, over here, or out of scale. The maths to do that can get actually quite complex, because now you're doing a regression considering the uncertainties in three dimensions, so the maths can be complex, very complex algebra. Lucky for you, lucky for me, lucky for all of us, you don't have to do it. You rarely find this approach followed in stalagmites. Why? Because you have to get a lot of samples. It's complex, it's expensive, not very common to find it for stalagmites. So I found this paper by Bernal. They're dating pedogenic culprits, very similar to what we do. They have highly variable compositions of uranium and thorium in the detrital material, and you can see these plots, like really how these plots really nicely in a 3D space. These plots are actually quite difficult to make, but they plot really nice. This is the composition of in secular equilibrium. So you can see that some samples of the detrital material is definitely not plotting within the fields of secular equilibrium. Can you do that in isoplot? Yes, you can do that in isoplot. This is data from this paper that you can also find in the folder. You just go to evolution, but then you say calculate an isochron H and propagate its technical uncertainties, and boom, this is what you have. What is it? What kind of plot is this? This is the evolution diagram. These are the measured samples that are being just, imagine that you're just looking this on 3D, and these are above this. This is the isochron, and this is the isochron intercept. So this is actually projecting into this into this area, and this is actually giving us the isotopic composition of the detritus free sample, and actually giving us an H. So, what do you know now? We know that all carbonate samples are dirty, all of them. All stalagmites will have some degree of thorium-232. There is no way, if you have thorium-232 introduce it into your sample, basically means that you also introduce some part, of, at least a tiny part of uranium or thorium-230. A 2-point isochron will work great in most cases, particularly if you have low thorium-232. If that's not the case, you have to do an isochron. What most people actually do is that I've worked with, if their samples have a lot of sodium, they get, why bother? They just discuss. I'm not like that. I like the geochronological challenges, so that's what I recommend also working with the isochron corrections and getting into it. So now you have to build an H model. You do that. How you do that? An H model, a mathematical function that assigns an H to each sample based on the measured distance, either from the base or the tip of the stalagmite. And this is very important because basically this is what you are dating samples. This is because this is the most important part, the culmination of your dating. This is an H model. These are sorry, this is not an H model. This is just a plot of distance against H, corrected H. An H model is basically an equation on a form that will give us a relationship between distance from the tip or depth and its corresponding H. An H model should be monotonic. Basically means that has to increase with H has to increase with depth. And the other important thing is that not single point is independent. Even though you dated this independently, they are not completely independent because, well, growth rates don't vary like quite significant. They're not very variable in stalagmites. So they're kind of related. So the other thing is you spend hundreds and hundreds and hundreds of hours micro-drilling your stalagmite, doing laser ablation, whatever, but you have hundreds, if not thousands of points you have to assign an H. But you only have a limited amount of dated positions. So what do? You have an inversion. A linear interpolation, it works fine. Sometimes it's done. These inversions are, what do you do with them? And then we spend a lot of time working with the uncertainties and minimizing the uncertainty of the contribution of the detractor material. And then suddenly, are we going to ignore that? We cannot ignore it. We have to take it into consideration. A linear regression looks nice, a polynomial equation looks nicer, but still it's not fitting perfectly. So there are two options to work with. One of them works with R, which is stalage, and the other one works with MATLAB, which is Copra. Basically, they are considered all the H uncertainties, and they actually see how are these translated into the time series. And they can handle the presence of hiatus, and they actually use an objective methods to actually detect whether there's an H inversion or if there's a problem with the dating. It should stay or should they go? The stalage, I was going to show you how to run it, but we're running out of time. So basically, it requires two files. One of them with the age and the depths of the samples, and the other one with the depths of the how many of the sample props. Builds a preliminary H model. Basically, it tells you, tries to detect whether you have major or minor outliers. Fit line between the points. Makes what it's called a Monte Carlo simulation. Basically, I'll show you in a second. Basically, makes a lot of simulations. Assesses all the possible lines that can fit within the uncertainties, and then goes and it starts growing. And I'll show you in a second how does it look like. So this is in R. So it's actually running. Oh, come on. Yeah, okay. So it starts running, and this is the H model. Starts working with the H model. The only problem that has SLH is that it only runs on old versions of R. It doesn't work only with R with the graphical interface. It runs on version 2.1, I think. But other than that, it works really, really nicely. And these are all the iterations that is actually doing to actually calculate. And this is your H model, basically what it has. What do you get? You get a text file with an x, y plus, a y plus and y minus, the consecutive sample number, the depth of your proxy sample, the median age for that f, the maximum age, the minimum age, and you can then have an H model. This is really an H model because it's actually giving you an age for each, an age and an uncertainty for each sample point of your proxy. On the other hand, Copra, you can get Copra from here. Copra also works, has a little bit of a problem that works on early versions of MATLAB 2014. People have told me that it works also on modern versions, but not the graphical interface, I think. I've only managed to run it in this version of MATLAB. And basically, Copra has a this multi-color approximation that it calculates all the possible routes and then based on the uncertainties that we are providing to the system, and it actually translates these uncertainties to the time series and to the actually the proxy. The other advantage that Copra has over SLH is it actually allows inclusion of layer counting. So if you have layer counting because you spent several hours counting layers on your 800 years stalagmite, you can actually include this in the H model, or if you have layer counting by band counting because of strontium variability, you can also include this in the H model. So this is how actually Copra looks like, and I'm going to run this. It doesn't seem like it's doing anything because when I was doing the screen capture, it's not capturing the other windows that are showing up. But this is, I'm loading here a text file with the data, a text file with the proxy details. Here the main difference is that I'm including the depth of the sample and the value of the proxy. This it plots an initial H model. I remove one H inversion, and it actually calculates all. This is all the possible solutions that calculates. It's actually calculating 2,000 solutions for that H model, and how these uncertainties are actually translating into the into your time series. Whether you like it or not, whether you like it or not, it's up for discussion because it is actually introducing more variability than they actually observe into the time series. It really depends on you to decide how to do it. This is what you get from Copra. Plot, you can get plots in JPEG format, and also the maximum age, the medium age, and how the proxy is actually being affected. A comparison with same data set between installation and Copra. They look fairly similar. You say, yeah, exactly the same. Once you put them one on top of the other, say, yeah, exactly the same. It doesn't really matter. There's actually, at least for this data set, a little bit of difference. I'm plotting here the difference between the H difference between Copra and SLH. There appears to be a systematic difference in Copra. It's something that, at least is happening with this data set. It's something that has to be assessed, fully assessed with whatever you're working. And there's some border effects. Basically, here Copra is actually putting the line here, and SLH is actually going straight. There's some changes here that has to be worked on. Pretty nice spot. But basically, just to wrap it up on the H models, your whole record, whether it's a trace element, whether it's whatever you like, your whole record hinges on the robustness of the H model. So it's something that you have to really, really work, really understand really well what you're doing. It's very, 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 very important to assess whether the uncertainties are affecting your conclusions or not. You're going to be asking, okay, what software is better to make an H model? it really doesn't matter, because if your conclusions are based on using COPRA, or using SLH, or using a linear interpolation, they are not really robust conclusions. If your conclusions are based on the software that you're using, if your paleoclimatic conclusions are based on that, then they're wrong. They're not really robust. You have to find a way to make it more robust. And that's something that is very, very clear. The other very important thing is something that Sebastian Breitenbach put in his paper, says, the usually dated samples and their geochemical behavior, the mineralogical and petrographic environment should be evaluated by the specialist. Information on sampling depth, possible contamination, hiatuses, geochemical alterations might be available and can greatly help identify outliers prior to modeling. So it's very important. You have to put everything that you see in the stalagmite, you have to consider it further before jumping into the wrong conclusions. So just to finish up, who's going to go to a uranium-thorium dating lab soonish or later? Some of you might go, yes. What to know, what to expect. It's not cheap. It's about $300 per sample, or even more. So you better make your time and resources get the best, most value. So if you have uranium and thorium concentration of your sample prior to send it to the lab, it's better. Why? Because it'll tell you what to expect. If you have no uranium and lots of thorium, then might as well get some other samples. You don't want to spend $500 to tell you, so someone tells you your samples are undatable. Get digital images of your stalagmites, high resolution and with scale. This is very, very important to know whether there's some petrographic information there, there's some porosity or something like that, so you can later discuss. Very important, make sure that your samples arrive before you, or at least with you to the lab. When you're doing uranium thorium dating, it basically means that you have to be very, 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 very consistent on what you do. All the samples are treated exactly the same, so you know that the tiny difference that you can see are actually because the samples are slightly different, not because you did things slightly different. So you have to be extremely consistent in everything you do in the lab. Yes, you will be working with radioactive material, and that basically means that there's you'll be exposed to radiation, but it's tiny, extremely, extremely, extremely tiny. You'll get more radiation by eating a banana, and I'm serious, than by working in a uranium series lab. Unless, of course, you decide to eat your samples. But nevertheless, so the lab manager or someone in the lab will have worked on developing the safety protocols. Stick to them. Do not improvise. You will be also working with acids, bases, and peroxides. Always wear your protective clothes. You will be working with an ultra-sensitive gravimetric method, isotope dilution. So never, ever, ever touch your sample without gloves. Ever. Write everything, label everything. That's very, very basic, very important. You need to be focused on your samples. So we usually say tell students that are coming to the clean lab just to forget about life, enjoy the clean air, relax, put some music. Very important, manage your caffeine intake. And I'm serious. Why? Because you will be pipetting into different into different columns, and if you take 5 cups of coffee prior to your lab work, you'll be like. So, and I'm talking about experience from experience. So yes, manage. And finally, working with the mass spectrometer. I don't know for you, but for me, first time working with Neptune, mass spectrometer was daunting. It was just like, this is huge. The instrument will not bite. The instrument will not explode. But stick to the protocols that are secret to each lab. Each lab, you might have experience working in Larry Edwards' lab. The protocols will be different if you're working with high chain, and the protocol will be different if you work in my lab, and the protocols will be different if you're working in Germany and everything. Why? Because each instrument has slight differences, and you better stick to those protocols. There's a long work behind sampling those protocols. And yeah, thank you very much.
Thank you so much for such an interesting and comprehensive lecture. Unfortunately, we don't have time for the questions now, but I invite everyone to ask and discuss later during the lecture session. And leave the floor to Ben, who will introduce our next speaker.
Thank you so much. Is there going to be using Dr. Sean? Oh, there he is.